Okay, let's continue. So we were talking about indefinite time horizon game. Okay, now the Prisoner's Dilemma is played for indefinite many times. Okay, then in this case, what we want to consider what condition will make the cooperation sustainable to keep the cooperation. Okay, so this is actually a really hard problem. It took a lot of the economists study this for quite a long time, but we're not going to go to the full picture. We're considering a specific equilibrium here using the so-called trigger strategy. Okay, so the trigger strategy goes like this. This strategy says that if I'm using the trigger strategy, then my strategy is I will stay silent as long as the other player stays silent. Okay, so don't understand this?
But if you say something and the opponent makes the same strategy, then you both remain.
What?
Like you say, you have to wait until the other goes silent in order to go silent.
No, I'm only saying that I will go silent as long as I observe that in the past you are all silent. And if this is first round, I will go silent because I don't have an observation. And if I observe that in one of the previous trial, in any of the previous trial that you confess, I will confess. Okay. So do people understand this strategy? Okay. The reason why this is called trigger strategy is the action of confess is just like a trigger point, right? As long as someone confesses, it changes everything. As long as someone confesses, because if both players are using the trigger strategy, if someone deviates from silent to confess, then everybody will simply start it to be, everybody's confessed now. Okay? Yes?
So you have to know that the other person has confessed.
We will be able to observe all the previous action, previous history. That's the assumption here. Yeah.
And we consider that the other knows that the first one is confessed. Like every time.
That's what she asked. Just whether we observe the history. Yeah. We do observe the history. Yeah. Okay? Okay. If both are using a trigger strategy, the obviously result would be both would keep silent until the end. Do we agree? Right? Okay. But in order to show that both players using the trigger strategy is a Nash equilibrium, we need more than that. What I just claimed is that they both use the trigger strategy, they will both stay silent from day 1 to day infinity. But that's not enough to show that this is a Nash equilibrium. Actually, this is not related to showing that it is a Nash equilibrium at all. Okay? To show that this is a Nash equilibrium, we need to show that there is no incentive to deviate. Okay, so what's the benefit of one deviation? So consider at some point time t, you are one of the players. This is symmetric. Both players are using the trigger strategy, so you only need to consider one player. If you're player B and you're thinking that I want to confess this round, what would actually happen? What would actually happen is I will, instead of -2 at this round, I will get -1. We were here, right? Both are silent. if I move to confessed, I get -1, right? So instead of -2, I will get -1. However, I will get -3 in the next round, and the next round, and the next round, and from now on. But here, I will. So let's write this first. Sorry, this one maybe the math is a little bit tricky, so it's not easier to see. Not easy to see. So if I still keep silent this round and so on, I only consider the deviation at this round. Okay, then this round I will get -2. Next round I will get -2. The next round I will also get -2, and so on. Right? And because each round is continued with a probability g, so this one is probability g. This is g power to the power of 2, and there's another -2 here. Then it's g to the power of 3, and this is 1. So this times this times this, and aggregating together, this one gives you this one. Are we clear? Very good? Okay. And if I deviate at this round, I will actually get -1 this round. But because I confess this round, from now on our equilibrium would be confess and confess from now on forever, right? So next round I will get -3. Next round I will get -3, and so on. This is with probability 1. This is with probability g. This is with probability g power to the power of 2, and so on. So again, this times this and add it up together, it gives you this. Right? Okay. Now the key is how to calculate this. Okay. This one actually equal to okay. But if you don't understand how you get this, so what we want to derive is this. Right? Let's call this capital A. What is g times capital A? That would be -2 g plus g to the power of 2 plus g to the power of 3 and plus g to the power of 4 plus ... Right? Okay. And from here, you know that A equals to -2 plus -2 times g plus g to the power of 2 plus g to the power of 3 plus g to the power of 4 plus blah blah blah. I just multiplied this inside. Is that clear? Okay. And this part and this part are the same, right? Actually, including this part. So I can rewrite this as GA. And then I will notice that 1 minus G times A equals -2. So from here. And then you can derive that A equals to 1 minus G minus 2. And A is what we originally want. So you find that this one equals this one, just as I wrote it here. And actually, you should have already learned this in your high school math somewhere, or at least college math. So basically, the formula is 1 minus the common ratio over the first term. So here, the first term is minus 2. The common ratio is g. So it's 1 minus g over minus 2. Similarly here, this part, the first term is minus 3 times g. But the common ratio is also g. So it is 1 minus g. And the first term is still minus, this one is still minus 1. So it's this minus 1. Okay. Yeah, so since we can translate this into 1 minus g over minus 2, and this part translate into 1 minus g minus 3g, and we want this one to be bigger than that one. Basically, keeping silent better than deviate from silent, right? And and minus 1. Forgot the minus 1 here. So basically, to solve for this implies minus 2 greater than minus 3g minus 1 minus g. And then this part equals to minus 2g minus 1. So minus 2 greater than minus 2g minus 1. This implies 2g is greater than 1, which implies g has to be greater than half. Okay? So as long as the probability of continuation is high enough, then in this case, high enough means greater than half, then there's an incentive to cooperate or keep using the trigger strategy. So this proves that trigger strategy can be a Nash equilibrium. Both people use the trigger strategy. Can be a Nash equilibrium as long as G is greater than half. Okay? And this is actually not the only one strategy that can sustain cooperation in a infinitely repeated game. Sorry. The other strategy is called T for tat. Okay. In T for tat, basically, I will do what you did in the last round. So if you confess in the last round, I will confess this round. But if you're silent last round, I will silent this round. And in the first round, I don't have history observing you, so I will do silent. And that's why the first round, if you both use T for tat strategy, in the first round you were silent, and the second round you're also silent. But again, this one does not guarantee that if both people use T for tat, it will imply a Nash equilibrium. You still need to do a similar check, like I just did for the trigger strategy. Or they also call Grimm strategy or Grimm trigger strategy, the same one. Okay, but that's not the main point in this course, so I'm not going to illustrate that. But the idea should be pretty clear now. How to derive this should be pretty clear. Okay? Okay. Now, I want you to not think of game theory as like following. So everybody is using some action space that's discrete. So someone either choose confess or silent or ballet or boxing or some meeting point A, meeting point B or whatever. Or matching pennies, that's going to be heads or tail. Okay, so actually game theory can also apply in situation where the decision is a continuous space, continuous action. So let's consider the following game called Tragedy of the Commons. So suppose there are two shepherds, A and B. They both raise sheep. And shepherd A raised, the number of sheep he raised is SA. And for B, that's shepherd B, that's SB. Okay. And the benefit from one sheep, or the price, the market price of one sheep is 120 minus the total quantity. Basically, this is minus SA plus SB. So as you know, the higher the quantity, the lower the price. That's the market rule, market demand rule, right? So this is a linear demand function, basically. And so the total benefit of raising SA and SB sheep for shepherd A and shepherd B would be the number of sheep he raised and the price of each sheep. That's the benefit from the sheep. Assuming that raising the sheep doesn't have any cost. Okay, I'm not talking about cost here. Similarly, for shepherd B, that's going to be SB times 120 minus SA minus SB. Is that clear? Okay. And if that's the case, the marginal benefit from raising one sheep would be the following. How do we derive this? So for shepherd A, remember the total benefit is this. And the marginal benefit of raising another sheep is basically the whole thing taking a derivative of SA. Okay? And inside you can rewrite this as 120 SA minus SA squared minus SASB. Right? The derivative with respect to SA after the derivative with respect to SA, it will be 120 minus 2SA minus SB. That's just calculus sort of 1-to-1, which gives you this. Is that clear? Okay. Similarly, for shepherd B, we can derive that the marginal benefit from raising one sheep would be 120 minus SA minus 2SB. And the general idea of maximizing utility or maximizing benefit would be to find where the marginal benefit meet the marginal cost, right? You should learn this in microeconomics or my economic 101, principle of economics, somewhere that. So basically you set the marginal benefit equal marginal cost. And the reason why it is 0 here is because I said that there's no cost raising sheep. Okay? And so this is basically where the two equation that the optimal solution must satisfy. Okay? And since we have two linear equation and two unknown variable, we should be able to solve for SA and SB, which gives us that SA star and SB star equals 40. Okay, it's just from here. And a way to look at this is the Nash equilibrium that we found. Okay, SA star and SB star is the Nash equilibrium we found. And the reason why this is true, we can look at this as the best response function. So we can rewrite this function as like this. So we write SA as a function of SB basically. So these two equations are exactly the same, but just rearrange, right? Here, SA equals to 60 minus half SB. Remember, because this is shepherd A's decision. When shepherd A is making the decision of how many sheep he's gonna raise, he doesn't know SB. Okay, so SB here is taking it as a constant basically, a variable but constant. I don't care. I don't have control over that. So, but that's the other person's strategy basically, right? The other person's action, and here is also strategy. So what I do is how do I decide SA? My best SA that I can choose is gonna be what the other person choose times 0.5 or half, and 60 minus that. That's why this line is the best response function. And if you draw the best response function for the one I just draw, that's going to be this line. This is just, XY plan, and you use SA and SB as the X and Y axis, and you can draw this. And you can also draw the best response function for shepherd B, and you get this line. And remember, the definition of Nash equilibrium is where the best response meet each other. So this point is the Nash equilibrium. That's the 40-40. Are we clear so far? How to derive this 40-40? We're good? Okay. If so, one question. So why is this referred as the tragedy of the comments? What's the tragedy here? You should also learn this in the principal economic class, by the way. The tragedy part is basically they both raise too many sheep. Why do I say this? So, consider a social planner who can simultaneously decide how many sheep the shepherd A and shepherd B both raise. And this person decided that both persons would reduce the sheep to 30. Okay, so if they both raise 30, remember the price would be 120 minus 60. So the price will be 60. And they both raised 30, so each of them would earn 60 times 30. Right? But in the current setting, where they raise 40, the price is 120 minus 80, which is 40. And price times quantity, they will 40 times 40, that's 106, so 1600, which is lower than 1800. So if they both reduce the number of sheep, they will actually both benefit from that result. Anyone care to explain to me why they didn't do so?
Why they didn't reduce?
Yeah, why they didn't reduce.
Because if one reduces, the other is gonna raise more ships.
Yes, that's called free ride. Okay, that's called free riding. You can actually calculate if the other person raised 30, like the optimal case. If the other person raised 30, that means here it is 30. Then the best response for shepherd A is actually to raise 60 minus 15, which is 45. So they will raise even more than 40 sheep. Okay, that's why they cannot reach the optimal solution. Okay? Any questions? We basically finished the theoretical part of game theory, and we're actually going to the behavioral part, or the main part of game theory that is more important for this class. So make sure you understand the theory part first. We good? Okay, so if we're good, then we will first play some games.